All right, so let's take a look at question 3, part B. This is question 3B from the 2011 scholarship paper. Part A is in a separate video because it was quite involved itself. So in part B, we're looking at reduction half equations. We're talking about the different oxidation states of manganese. We can read the context of the question up here. Manganese is an element that exhibits a number of different oxidation states. Half-cell reactions potentials for the different oxidation states vary depending on the conditions. The table gives the standard reduction potential values for manganese species in aqueous solution ranging from Mn2 plus to Mn7 plus at pH 0 and at pH 14. So there's pH 0 right there, and then pH 14. This is based on the old level 3 content, which used to ask you to predict whether a reaction was spontaneous or non-spontaneous. In other words, would this reaction happen in solution by itself without any external voltage or electrical current? I'm not sure if it's still fair game to assess this on any subsequent NCEA scholarship papers, but this content anyway is coming from the old level 3 NCEA course. So you'd be given a range of different half equations. All of these equations are showing the reduction of a species. So Mn2 plus is reduced to Mn by 2 electrons, and the E naught, the reduction potential value for that, is negative 1.19 volts. So all of these species are being reduced by some number of electrons, and then you have the reduced species then on the right-hand side. To go in the opposite direction is oxidation. So this would be, from here to here would be oxidation. So oxidation from right to left, and reduction from left to right. So it's important to bear that in mind as we go through looking at each of these equations. The other thing is, because there are so many equations to deal with, we've just numbered them 1 to 11 for the box, and then there's 2 more equations you're given down here for the reduction of oxygen in pH 14 and the reduction of oxygen at a very low pH of 0. So the pH 14 results in the production of hydroxide ions, and the pH of 0 has a lot of protons, as you would expect. So the first question, part 1 here, is explain why manganese 2 plus is not oxidized by oxygen in solutions at pH 0, but is oxidized by oxygen in solutions in which you have hydroxide ions, which would be pH 14, this one right here. So we're basically considering reduction potential values, or E naught values, and we're comparing them to see if the reaction is spontaneous or not. So what we need to do here is, if we're looking at the first part here, which is explain why Mn2 plus is not oxidized by oxygen in solutions at pH equals to 0, then we need to consider this equation, which is equation 13. So equation 13, and we need to consider all of the following. So to oxidize Mn2 plus, we need to consider equations 3, 4, and 5, because if we just highlight this, you have Mn2 plus right there, Mn2 plus right there, and Mn2 plus right there. And as I say, if you go in the opposite direction, then this would be oxidation. So if you go in this direction, this would be oxidation of Mn2 plus back to Mn3 plus, Mn2 plus back to plus 7 in this case, and Mn2 plus back to plus 4 in this case. So we have to consider equations 3, 4, and 5 in conjunction with equation 13. So if you look at the NCEA guys, they just took equation 13 and equation, so they took equation 13 and equation number 5 because they were the easiest to deal with. But you can easily explain this or show this for any of the other equations. So I'm going to do equation 13 plus equation number 3, just to show that you can also show it that way, and equation 4, and then you can read the answer for equation 5 from the NCEA guys. So a new page. So what I've done here is I've laid out the 3 equations, 3, 4, and 5. These are written in the reduction format, so we're reducing manganese from plus 7 to plus 2, from, so that's not plus 7 there, that's plus 4 to plus 2, plus 7 here to plus 2, and plus 3 to plus 2. So reduction in all cases. E naught values are all positive because manganese is very oxidizing or has a high reduction potential. The oxygen has quite a high reduction potential itself here at the H equals to 0, and that value is plus 1.23 volts. It's being reduced from 0 here to -2 here. So by taking a look at equation 3 and equation 13, both of them actually have the same reduction potential. So by that fact alone, neither of them would oxidize or reduce each other. So there would be no reaction just based on comparing those two E naught values right there. So plus 1.23 and plus 1.23. So there would be no reaction between those two. If we were to actually write out the equation for the reaction that we're talking about taking place, so what we're saying is we're taking this reduction equation and reversing it, so then it becomes Mn2 plus 2H2O, so the manganese is being oxidized to MnO2 plus 4H plus 2 electrons. Don't change the E naught value, keep it the same. And then what we're going to do is, that's equation 3, which has been reversed. We're keeping the the oxygen equation 13 the same. So that's O2 plus 4H plus 4 electrons going to 2H2O. And the E naught value is the same there, plus 1.23 volts. That's equation 13. We want to get rid of these electrons, so we times off this by 2, so this becomes 2Mn2 plus, this becomes 4, this becomes 2MnO2, this becomes 8H plus, and this becomes 4. That will cancel with our 4 electrons right there. The 2H2O can subtract from that to leave 2H2O left over, and then our equation here, what we're suggesting could happen is 2Mn2 plus could be oxidized by oxygen there. We have 4H plus, that's subtracted from that to give you 4H plus there, so we get rid of that on this side. And the equation continues to give you, so just 2Mn2 plus oxygen, plus your 2H2O, forgot about that, going to 2MnO2 plus 4H plus. And the E cell for that, which is just simply the reduction potential for the reduction process, minus for the oxidation process. So this is reduction down here. This is oxidation up here. This is why we didn't change the sign, because the equation accounts for the fact that this redox equation has been reversed, so we don't change the sign right here. So then the E cell becomes 1.23 volts plus 1.23 volts minus 1.23 volts, which is equal to 0.00 volts, which means no reaction occurs. Non-spontaneous is the expression used in redox chemistry. If we take the same situation now, if we look at equation 4 and equation 13, so equation 4 and equation 13, okay, so I've just rewritten the reduction potential values here. I figure this is the easiest way to illustrate this in the simplest form. And we've just done equation 3 combined with equation 13, and the E cell for that becomes 0, which is non-spontaneous. If you take the reduction of oxygen being the plus 1.23 volts, so E reduction, this is equation 13 plus 4, then we'll have E reduction for oxygen as being plus 1.23 volts, and then minus the reduction potential for the oxidation reaction, which we're saying is equation 4 in this case, so that's minus 1.51 volts. And that becomes negative 0.18 volts, which again means non-spontaneous, so that reaction won't occur. And of course, we can clearly see that the species with the higher reduction potential is the one which will be reduced, and this process would be oxidized instead. So 13 and 4 non-spontaneous, and then the ones that the NCEA guys do, number 5 and number 13, again, the situation you have here is that if you're reducing your oxygen, then you have plus 1.23 volts for the oxygen being reduced, minus the 1.54 volts for the equation 5, which in this case would be Mn2 plus being oxidized to Mn3 plus. and that gives you negative um, minus point or negative 0.21 volts, which again is non-spontaneous. So you could write equations for this, but I think the use of reduction potential values is sufficient. We just look at the answer from the NCEA guys. So this is question 3B part 1. They haven't even looked at the other equation yet, but for the answers, let's go to the top here, B part 1. So they say, all the way to the top here, at pH 0, combining equations 13 and 5, so they chose these two equations. They work out that the E cell value is less than naught, which we just did there was minus 0.21 volts. They wrote the equation for manganese. You'll notice it's in the reversed. They've reversed the equation because they're talking about oxidation of the Mn2+, so you had to reverse the equation. They didn't change the sign of the reduction potential value because, as I say, that's accounted for in the E cell equation. And then they find an E naught value which is less than 0, so it's non-spontaneous. They just made a note down the bottom. Alternative answers could have been the MnO2 as a product, which is the one you get if you use equation 3 and equation 13. So you get MnO2 as a product. And as I've just demonstrated, you can also use equation 4 and equation 13 as well. So you could also do equation 4 and equation 13 as well. So that's that part of the question. Then you need to look at pH 14. So let's take a look at that. So for the second part of that question, we'll just look at the question again here. It said, explain why Mn2+ is not oxidized by oxygen in solutions at pH equal to 0. We just did that. The second part of the question, I'll just highlight in a different color. It is oxidized by oxygen solutions in which OH minus is present. So that's at pH 14, which is equation 12. So we need to consider equation 12 as being the reduction of oxygen again, but in alkaline condition. And if the oxygen is being reduced, then the other species we're looking for is the oxidation of Mn2+ at pH 14, and there's only one equation. If you look here, the oxidation number of manganese is +2, and then it goes to +3. So we're considering equations 10 and equations 12 for this second part of part 1. So I've laid them out here. We have equation 10 here, and we have equation 12 right here. So if you look at the reduction potential values here, you can clearly see that the one with the higher value, which is the reduction of oxygen to hydroxide ions here, is will take place, and then the Mn2+ in its hydroxide here will be oxidized to Mn3+ in its oxide. So this reaction is spontaneous, and you can demonstrate that by just rearranging the equation. So what we're talking about here is the 2Mn manganese hydroxide, and we're oxidizing it, so we want to write the oxidation equation here, going to 3H2O plus 2 electrons. We keep the E naught value the same because the equation deals with that change. The oxygen equation is right here. It is being reduced, so this does happen, and you get 4OH minus, and the E naught value at pH 14 is equal to plus 0.40 volts. The E cell for that, we better just finish the equations first. Getting ahead of myself there. Let's finish these equations off. So we have 2 electrons here and 4 here. So we times the top one by 2. Everything by 2 up here, and that will become, so this becomes 4. Multiplying everything by 2, that becomes 4. This becomes 4 hydroxide. This becomes 2. This becomes 6, and this becomes 4. Your 4 electrons cancel with those 4 electrons right there. You can subtract those 2 waters from that to leave 4H2O. And your 4 hydroxides cancel with your 4 hydroxides. So your final equation there is going to become 4MnOH2 plus oxygen, and all of that is going to 2Mn2O3 plus 4H2O. The E cell for that one then is equal to the reduction, the E naught of the reduction minus the oxidation, which in this case, the oxygen is being reduced, so that's plus 40 volts minus negative 0.23 volts, which is an addition, which gives you plus 0.63 volts, which is spontaneous. And so this is why manganese is oxidized by oxygen in solutions which have an alkaline pH. So that answers question B, part 1. Okay, for B, part 2, I just want you to have it printed out or on a separate page in front of you. I'll read through the question now, but I really wanted to have the equations in front of me as I read through it. And I've highlighted the 2 equations which are relevant here, equations 2 and 7. So B part 2 reads, KMnO4, potassium permanganate, is a common oxidant, and that's because it has such a high reduction potential or E naught value. And in acidic conditions may be reduced to MnO2, manganese dioxide, or manganese 2 plus ions. So the question continues, discuss why the intermediate species HMnO4-, which is known as permanganic acid, does not accumulate during the reduction of MnO4- to MnO2. So what we have here is a situation where, first of all, MnO4- is reduced to HMnO4, MnO4-, and this would be considered an intermediate species right here. So this is the permanganic acid, which is an intermediate species. Okay, I'll just change the thickness of that pen. So the question is asking you, on when permanganate is being reduced all the way to manganese dioxide in equation 7, how come this permanganic acid doesn't accumulate and en route to producing MnO2? So that's the question we're asking here. So again, we're comparing 2 equations, in this case equation 2 and equation 7. So I've laid them out here, equation 2 and equation 7. So just to repeat the question again, because it's well illustrated when you have the 2 equations identified, we're asking why, when you're trying to convert your permanganate to your manganese dioxide, why is it that this intermediate here, the permanganic acid, doesn't accumulate? So what we're really saying is why, when you're trying to convert your permanganate to your manganese dioxide, does this reverse reaction not happen? Why does this reverse reaction not happen to produce permanganic acid? So again, it's a case of spontaneity. So we're saying that this would be the reduction process, and we're saying that this should be the oxidation process because we want it to go from MnO2 back to permanganic acid. So for that to happen, of course, the reduction potential here should be less than the reduction potential for the permanganate going to the permanganic acid, which it's not. So we can see straight away that it's not spontaneous, just from comparing the E naught values there. But we can do the equations out and work out an E cell for this. So what we have here is we want to reverse this equation at the top. So we want to reverse this equation, and then we'll have HMnO4- going to MnO4- plus H plus an electron, and then the bottom equation keeps it as it is because we're hypothetically saying that that is the reduction equation. Or it is the reduction equation if you base it on the numbers that we have here. MnO2 plus 2H2O. So then we want to just even the electrons out. So we have 2 on the bottom, so we multiply this by 2 here. So we have 2 permanganic acid, 2 permanganate, 2H plus and 2 electrons. And then we add those equations together. We have 3 permanganic acid there, HMnO4-, plus your 3H plus, subtracted from that, you get 1 left over. that's going to your 2MnO4 minus plus MnO2 plus 2H2O. The E cell for that, then, this is the reduction, so E naught here is equal to plus 2.10 volts, which we said from the largest value here is the one which is reduced. The E naught value up here is equal to plus 0.90 volts, which will be the oxidation number. So it's plus 2.10 volts minus 0.90 volts, which is equal to plus 1.20 volts, which is spontaneous and does happen. So the equations which do happen are that the permanganate acid is oxidized to permanganate if it does form, and then the permanganate acid, if it does form, it'll be reduced. So I'll repeat that again. That didn't make sense at all. So this equation shows that if the permanganate acid does form, it will be converted back to permanganate and the manganese dioxide. So in which case the manganese dioxide is stable in acidic conditions. Or put it another way, the permanganate acid does not accumulate. Doesn't accumulate because it is converted into MnO2 and MnO4 minus at that in those conditions. So for B part 3, they want us to discuss the pH dependence on the stability of Mn3 plus in aqueous solution. So let's look at the equations that we have to look at here. So pH, we've got to consider the presence of Mn3 plus at pH 0 and at pH 14. So if we look at the presence of Mn3 plus at pH 0, first of all, we're talking about equation number 5, Mn3 plus right there, and equation number 8, Mn3 plus right here. So we're basically trying to determine what species will exist if the pH is acidic, essentially very, very low at pH equals to 0. So we're looking at equations 8 and 5. And if we look at the E naught values here, the one with the highest reduction potential is the Mn3 plus being reduced to Mn2 plus, which means we must rewrite this equation in reverse. So it's going to be Mn3 plus 2H2O going to MnO2 plus 4H plus an electron. And then the E naught value, we keep that the same, don't change its sign, never change its sign. Mn3 plus, the second equation, number 5 there, is kept the same. It's the one which is reduced, Mn2 plus, and then we add these two equations together, and we get 2Mn3 plus, and those electrons cancel each other out, plus 2H2O going to MnO2 plus Mn2 plus. So at the low pH, the species which will exist will be the MnO2 and the Mn2 plus. So the Mn3 plus is unstable at pH equals to 0. The E cell for that then is going to be equal to the reduction one, which was the 1.54 volts, minus the oxidation one, which was 0.95 volts, which gives you an E cell value of positive 0.59 volts, which makes it spontaneous. Again, verifying that it's these two species which exist at low pH. If we look for pH 14, go back up there for a second. So pH 14. So for pH 14, I've identified that we need to consider equations 9 and 10, but I'll show you how I came up with that. So if we look at pH 14 here, and we want to consider the oxidation state of Mn in its 3 plus state, and that is going to be here. So it's plus 3 here. I'll reduce that marker size. So it's plus 3 right here, and also it's plus 3 right here. So the equations you want to consider are equations 9 and equation 10 for this last part, the stability of Mn3 plus at pH 14. So we're considering equations 9 and 10 here. And then the same thing again, look at the reduction potential values. The one with the higher value should be the one which is reduced. So we keep the top equation the same. and we'll have to reverse the other equation because it's the one which will be oxidized. So the E naught values, we never change them. That's equation 9, and that's reduction. And then we take our other equation and reverse it. So this equation is going to be reversed. So we have 2MnOH plus 2 hydroxide ions going to Mn2O3 plus 3H2O plus 2 electrons. The E naught value, we don't change anything there. It's negative 0.23 volts, and this is our oxidation half equation. We add those two equations together. We eliminate our electrons. Our 2 hydroxides also cancel. Our 3 waters, you can subtract 1 from that to leave 2 water left over there. So we have 2MnO2 plus 2 manganese hydroxide going to 2Mn2O3 plus 2H2O. And then we want to work at the E cell for that. The E cell for that will be equal to so plus 0.15 volts minus 0.23 volts, and that will give us an answer of plus 0.38 volts. So in this case, the species which are present will be the Mn2O3 and water, and this is where it's plus 3. So Mn3 plus will be stable or present if the pH equal to 14, whereas before it was absent when the pH was equal to 0. So it was changed from Mn3 plus into plus 4 in this case, or plus 2. So that's your answer to question 3b, part 3. So what I found so far in the scholarship papers, the redox questions can be quite tricky, but in this case, it was just the key to unlocking the question was understanding the idea of predicting whether a reaction was spontaneous or non-spontaneous.